What's going on? No questions? Okay, go ahead. Yeah. Yes? Number 17. Use the method of cylindrical shells to find the volume generated by rotating the region bounded by the given curves about the specified axis. 17? So you have y is equal to 4x minus x squared. What is that? All right, so we want to rotate this about x is 1. All right, so we always start with the picture, right? So let's try and graph that. So did you try graphing that with your calculator, parametric? No? Did you use your calculator for that, or just do it by hand? Okay, so for those of you who have tried the parametric mode on your calculator, hopefully you're comfortable with how you could graph something. Oh, wait, you don't need parametric for this. Never mind. But you're comfortable with parametric? Okay. All right, so we have a parabola. And if I were graphing that parabola, I would probably start out with the x-intercepts, maybe. I know it opens down, right? So what are the x-intercepts? I could set it equal to 0. All right, factor out an x, something like that. Well, I'm trying to graph it. I'll figure out where it hits the other one in a second. So 0 and 4. So I know that this graph hits at 0 and positive 4. I know it opens down, right? So it's going to look something like this. Oh, wow. Right? And then I have y equals 3. So that's up on the y-axis, 1, 2, 3. I'm going to assume that it's going to be somewhere in here, like this. Right? That's y equals 3. This one is y equals 4x minus x squared. My axis of rotation is x equals 1, which maybe is part of the reason why you might be, no, that's okay. What I'm hoping is that this little region, this is the region that we're talking about, we're going to rotate. I'm really hoping that it lies to the right of that line, which it should. But if that line cut through the center, we didn't talk about that, right? We didn't talk about how you rotate something about an axis if your region is on the axis of rotation. So that hopefully won't happen. So let me go ahead and try and figure out where those two hit each other, which would be at these 2 points. So to do that, I set the two functions equal to each other. That's where I'll do this over here, intersection. So I set, bless you, 4x minus x squared equals 3. That's a quadratic equation, so I'll move everything to one side. So if you move everything to one side, and I moved everything to the right side, and set it so it's equal to 0, and then I look at that, I just want to factor that. So I'll use just my kind of guess and check method here to try and factor this. I'm getting -1 minus 3 in there. And then set each of those factors equal to 0, you get 1 and 3. So that axis of rotation right here, 1, is exactly where that point is, which is kind of what I thought was going to happen by drawing it. But now we can be sure of that. All right. So with that in mind, I'm going to kind of redraw my picture just so I have a better idea of what's happening. Here's 1, axis of rotation. I have this point here, goes like this. Then I have my other one that goes like this, right? That's basically it. I'm trying to rotate that about this x is 1. So it says shells, right? It says shells, but I think you could see from that that that's really the only thing we could do, right? Because if we try and go with discs or washers, our rectangles would have to go horizontal, right? If I drew a horizontal rectangle in here, and then the top and bottom would be the same function, so it wouldn't work. So this is one of those examples where shells would be our only option. So I'm going to draw just an arbitrary rectangle in here, right? And I got into the habit, I think, with you all to just draw everything again. Like, here's my y-axis. Here's my axis of rotation. Whoa. Here was my rectangle that I'm rotating. We had the top function, and then we had the bottom function, like that. We're going to go around. So the top and bottom are pretty clear, right? In our formula, should I write the formula down, the volume? 2 pi, what was it, integral a to b, x, or what we said was the radius, right? That's the important thing. This x was actually the radius of our rotation. Radius. And then it was the top minus the bottom, right? Well, let's just see first, okay? Let's get what we have, and then we'll compare it to, you mean the book, the solution manual? Okay, well, let's see what we get. We have, our top and bottom are pretty clear, right? The top is the 4 minus x squared, the bottom is the 3. Now, it's just a matter of our radius. So our radius, we go up here and we look at, from our rectangle, we're saying, what's the distance from there to here, right? Or you could say, what's the distance from here to here, right? So what is it? 1 minus x? Any other options? Let me turn this off. X or 1 minus x, that's what I'm hearing. Anyone got anything else? Okay, so let me help you here. What is the distance from the y-axis all the way over to our rectangle? What's that distance? That's x. Okay, it'll always be x. From the y-axis to our rectangle, that's x. Okay. What is the distance from the y-axis to this? It's 1, right? So what is the distance from here to here? X minus 1. Isn't it? It's that distance x, then take away 1, it's x minus 1. Is that what you had? Is that what you had in yours? Yes? Okay. So x minus 1 is our radius. So we should have here 2 pi integral from, where were our points of intersection? 1 and 3, right? So 1 to 3. And that, remember, I'm getting that off of this, right? Here was this first point, 1, and the second point right here was 3. So I'm going from 1 to 3 of x minus 1. And now your top function, 4x minus x squared, and then minus your bottom function, which would be minus 3, and then dx. Now, you said the book had it wrong, or did you do 1 minus x? Okay, now you see why it's the other way? Okay. Those are those little things we have to be careful with on the test, right? It's figuring out that radius is one of the most challenging parts of these problems. So I recommend always drawing this out. And that way, when I'm looking at your work, I can kind of see if you had the idea down or not. You can't just kind of randomly guess at it. I'm not saying you did, but, you know. And then how did I say you could check to see if this radius is correct? Yeah, why don't you try the two endpoints? If you let x be 1, right? That means you are, in your picture, You are at this far corner, aren't you? X is 1. And what's your radius there? Well, you're actually on your rotation axis, aren't you? So the radius would be 0. And that's what happens when you plug 1 in right here. You get a radius of 0. Now, if you plug in 3, we get 2, right? Now, if I go up here and I go to 3, then what's the distance from here to the axis of rotation? 2. So it matches. If you had done, what did you have, 1 minus x? Then when you plug in 1, you would get 0, right? But when you plug in 3, you get negative 2. And so that would change things. Okay, good question. And then you evaluate that and get the rest of it, right? Just distribute out. Okay, what other questions were there? That was, you had the same one? Okay, good. 25. Set up the integral, and then it says use your calculator, right? So like Wolfram alpha or something like that. So we have x equals the square root of sine y. We're given that 0 is less than or equal to y is less than or equal to pi. Given that x is 0, and we're doing this about y equals 4. So maybe you're having a little trouble with what the square root of y would be. Or how did you do that? Did you use a calculator for it, or so just trying to do it by hand? Okay, so let me try and help you with the graph of this. We are stuck between 0 and pi, right, on the y-axis. And our sine here is a function of, or actually our x is a function of y. So we know that you cannot take the square root of a negative number, right? Can't do that. And sine does become negative, doesn't it? At some points, it does become negative. But if we restrict that y right here between 0 and pi, if you look at the sine function between 0 and pi, it is positive. So that's why we have this restriction. We have to restrict y between 0 and pi, or else this won't be defined. So let's just try and plug a value in for this. What would happen if we plug in 0? Sine of 0 is 0, right? Square root of 0 would be 0. So I'm going to do like a little t-table. Oops, whoa. A little t-table over here. If I plug in y, what do I get for x? We said if we plug in 0 for y, we get 0 for x, right? So that's 1 point on my graph. Now let's try another point. How about the other end point? Plug in pi. What's sine of pi? 0 again, right? So if I plug in pi over here for y, I get 0 again. So up here at pi, I'm at 0. And now try something maybe in the middle, like pi over 2. We plug pi over 2 in here. Sine of pi over 2 is 1. Square root of 1 is 1, right? So if I plug in pi over 2, we get 1. I don't know why my thing keeps doing that. It's weird. So here's 1 for my x. Pi over 2 is halfway. So 1. And so what it winds up looking like is basically the sine. It's like the first little arc of sine again, but going that way. And you could do more points, but just think about what does the square root do? You know? What happens when you take the square root of something? It still stays positive, right? Doesn't change the sign, right? If I take the square root of something, does it get bigger or smaller? Did we have this conversation already? I thought we had the conversation. If you take a number and square it, does it get bigger? We didn't have this conversation? You sure? Yeah, we didn't have that conversation? I thought we did. If I just say, hey, take a number and square it, does it get bigger? Not generally, okay? Sometimes it does, sometimes it doesn't. This is kind of a new thought here. So if I take the number 4 and I square it, it becomes 16. So squaring the 4 made it bigger. But if I take the number 1/2 and square it, it becomes 1/4, which actually became smaller than it started as, right? So if you square a number, it doesn't necessarily get bigger. It can get smaller. The only time it ever gets smaller is if the number is between 0 and 1. Now, it works the same way for square root. If I take the square root of 4, right, it gets smaller. But if I take the square root of 1/4, it gets bigger, right? So all that really happened here in this problem is that it's basically the sine curve, the normal sine curve. In fact, at this point, and this point, it's a normal sine curve. It's these points all here in this arc are a little bit bigger than they would be with a normal sine function. I hope this helps. We don't have to get too involved in the graphing of this, but I want you to kind of understand the number things going on here. Okay, is that good enough to start with? We happy with that? And then x is 0 is what? The y-axis, right? This. So our region that we're trying to rotate is this. And we're trying to rotate it about y equals 4. Where's 4? Well, what's pi? 3.14, so 4 is above that somewhere. And it's y equals 4, so it's a horizontal line of rotation. Here's 4 up here. We're doing this, right? Questions? All right. Washers or shells? Does it say? Does it tell you to do it a certain way? No, doesn't tell you. Can you do washers? If you try washers, remember with washers we said your rectangle would always have to be perpendicular to your axis of rotation. And if you try and draw this right here, right? What's wrong with that? The function on top and bottom are the same. So you can't use that. So you can't use washers. So we have to use shells. So we have to do it this way. Instead, there's our rectangle. We're going to rotate that around this way. I didn't show you an example of this in class, right? Everything that we did shells-wise was rotate around this way. So we never had to go this way, but we can. Same thing. All right? So help me out. What is the formula going to be? What is it going to look like? 2 pi integral. Here it will be 0 to pi, right? Because we're going to be going from this point up to this point because we're looking at the y's now instead of the x's. Now we would say like from C to D instead of A to B, but we'll just say 0 to pi here. And then it'll be the radius of rotation, which we're going to have to figure out. And then top minus bottom. For us, top minus bottom meant we turned our heads to the side, right? And went top and bottom like this. The top one is what? Square root of sine y, and the bottom one is 0, right? X equals 0. So I'm going to redraw this below. Here's my y-axis. I'll just draw my x-axis in there. Here's my rectangle that I'm rotating. I have that black curve here. This is x equals square root sine y. I have the bottom of, my rectangle needs to go all the way. Sorry. Goes all the way to the ground, doesn't it? The curve on the bottom is the curve x equals 0. My axis of rotation up here is y equals 4. Y'all okay with that drawing? Okay, so let's talk about this radius. It's going to be a little tricky. I always like to start by figuring out the distance. Well, in the previous problem, we started out by finding the distance between the y-axis and our rectangle, right? We said, what's the distance between that y-axis, right? Not the axis of rotation, but the y-axis and our rectangle. So now, instead of doing it that way, we're going to say, what's the distance between our x-axis and our rectangle? So what's this distance from here to here? It's y, right? It's the y coordinate. So this distance from here to here is y, right? What is the distance all the way from the axis of rotation all the way down to the x-axis? 4. And that means the distance from our axis of rotation to our rectangle, which is the thing we're interested in, is what? 4 minus y. You'll follow that? That's 4, take away y, that's your 4 minus y right there. So this is your radius of rotation. We have our top, we have our bottom, and then throw the 2 pi in, we're pretty much there. So I'm going 2 pi integral, you said 0 to pi, right? Radius of rotation, 4 minus y. Top was square root sine y minus 0. I don't need to put it, but I'm going to put it there in case you look back at these and you want to figure out, like, what was that all about. And then dy. And then to do that integration, believe it or not, I don't think we have a technique of integration that would be able to handle that. If we tried this, like if we distributed this through, right, basically just distribute this through to these two, our techniques of integration would fail. So using a computer to solve that would be the way to go. Mathematica has a pretty cool, I know Wolfram Alpha is pretty easy to do integrals, but Mathematica has these like templates. Whoa, here we go. See if y'all can see that. So you can just like put in 2 pi times 0 to pi, and then it was 4 minus y times the square root of y. Was that it? And then minus 0. So, oh, square root of sine y. It's thinking. It's still thinking. Interesting. Gamma functions. What does the back of the book have? Does it have a decimal? Did anyone check the back? Most people probably haven't ever heard of a gamma function, right? Oh, correct. 5. So they're going to give a decimal answer, I'm sure. Yes? So for Mathematica is giving me the exact answer. Like they're leaving it like if your answer was pi, they're leaving it as pi. So to be exact, they have to use these gamma error. They're like error functions. So if I put 2.0 in here instead and ask for it, so I just put 1 decimal, and anywhere in this problem, it's going to spit out the decimal. Is that what the book had? What is a decimal? Oh, it is this. Okay. So does that address everything on that one? We good? Okay. All right. Well, how about arc length? Did you all have any do any of those problems for arc length and run into the algebra of those? Simplification of the integrand, that thing under the square root, that stuff gets kind of ugly. No questions on that? I don't mind. On volume, which one? Pardon? Number 9? So still in the shells section? Oh, for arc length, number 9. All right. Wait, it was 9, right? Okay. So number 9 says y equals x cubed over 3 plus 1 over... I didn't do this one. It was similar to that. Okay. All right. That's fine. So we want to find the length of this arc between 1 and 2. All right. That's what we were trying to do. So we have a formula, right? That's all pretty much I gave you last time, arc length formula. The length of an arc is equal to what? Integral a to b, square root of 1 plus y prime, that thing squared, and then dx, right? So for this, all we need to know is its derivative, the derivative, and then the derivative squared. So I usually like to do that on the side because it requires a lot of work. So what is y prime here? Derivative of x cubed over 3 is x squared, right? And then the derivative here, just remember that this is the same as 1/4 x to the negative 1, right? And then I can bring power rule down, so negative 1/4 x to the negative 2, or you could write that as x squared minus 1 over 4x squared. Is that what you had? Is that what you worked with? I'll work with what you worked with. So that's the one you squared? All right. Any questions on that? It's just a derivative there. Y prime squared. So I'm going to take x squared minus 1 over 4x squared, x squared minus 1 over 4x squared, and I'm going to FOIL this thing out. So my first term is x to the 4th. That's this and this. And then now here to here, oh wow, they cancel out the x squareds, and you just get negative 1/4. And then the inside ones, negative 1/4 again. And then the outside ones, you get plus 1 over 16 x to the 4th. Did I tell you about the Cowboys? I've been trying to find the girl in the class that had the Cowboys jersey on that first day. Was that in this class? She dropped the class? Oh, I've been meaning to talk to her about her Cowboys. Because I was giving her a hard time on that first day. I was like, yeah, have a good season. How's that going for you over there? And now they keep winning. I was wondering why no one was rubbing it in my face. It's not here anymore. All right, so that's the derivative squared. Let's clean it up. I'm just going to make that minus, what's 1/4 minus 1/4? Or negative 1/4 minus a 4th? Negative 1/2 plus 1 over 16 x to the 4th. Okay, that's just derivative squared. Now let's go put that back into the formula. That's going to go underneath the square root and have a 1 added to it, right? Okay, here we go. So the arc length should be the integral. In this problem, we went from 1 to 2. Why? It was given, right? X was between 1 and 2. All right, square root of 1 plus all this. Can I put the 1 minus the 1/2 right now? Is that okay? The 1, I'm going to have a minus 1/2 right here. Can I just make it a 1/2? All right. 1/2 plus x to the 4th plus 1/16 x to the 4th, and then all this dx. So I'll just highlight it. Just remember that 1/2 came from taking the negative 1/2 here and putting it together with the 1 up there. All right, so I said last time, really, when you get to this point, you might look at that and go, what the hell? But I said, try and get a common denominator. That's usually what's going to work. So my common denominator is going to need to be 16x to the 4th. So let's try and make that happen. I'm going to have to multiply this first term by 8x to the 4th on the top and bottom. And then since this is over 1, I'm going to have to multiply it by 16x to the 4th on the top and the bottom. Right, just to get all common denominators here. So let me know if you have a question. Square root again. My new numerator will be 8x to the 4th, right? Plus 16x to the 8th plus 1. So 8x to 4th, and I'm going to put that in descending order. 16x to the 8th plus 8x to the 4th plus 1, all over my common denominator, which was 16x to the 4th dx. Any questions here? Oh, so your mistake was somewhere in here? Okay. I thought you used the 1 over x to the 2. That's why I went with that. But you did 1/4 x to the negative 2? So x to the 4th. Yeah, when you do this times this, that's x to the 4th. This times this, what'd you get there? I'm not calling you out, but... Okay, yeah. Yeah, these problems, man, everything has to be dead on, or else you're never going to get this thing to clean up down here. That's why I can't just like pick a problem and be like, okay, find the arc length. I mean, usually you won't be able to do it by hand. With the computer algebra system, Mathematica Wolfram, you can usually get it, but just in general, we have to pick them very, very carefully. So, all right, let me finish it up here. 16x to the 8th plus 8x to the 4th plus 1. We need to recognize that as being a quadratic type, and it factors to be two things, and it should be exactly the same thing twice. And what's good about that is we're going to have to be able to write that as whatever the factors are squared, and then the square root's going to wipe it out. But I need to go to a new page. So we have integral 1 to 2. So it's 4x to the 4th plus 1 times 4x to the 4th plus 1. Do you all agree? That's what that numerator is. Right, if I FOIL that out, I get back to 16x to the 8th plus 8x to the 4th plus 1. And like I just said, because there's two of those, that's the same as 4x to the 4th plus 1 squared, but then you're going to do the square root on top and bottom, so it'll go away. So we should just be at integral 1 to 2, 4x to the 4th plus 1 on top. And then we have to take square root of the bottom, which is 4x squared dx. And now you can split this into two separate fractions. So you can go integral 1 to 2, let me see, 4x to the 4th over 4x squared is just x squared. And then 1 over 4x squared is 1 over 4x squared dx. And you can just do power rule on these, right? Antiderivative of x squared. And then this one, bring that x squared up to the top as an x to the negative 2 and do your power rule. Do y'all have questions? I'm seeing a lot of... Maybe it's just a different perspective that I'm down here not standing up, but it looks different because y'all are like, what? So on most of the tests that you'll take, I'm going to be saying like set up the integral, but don't evaluate, right? On the arc length problem, you will have to evaluate all the way down to the answer, because that's kind of the point of the arc length problem is, you know, the fact that you can set it up and simplify the integrand to a point that you can integrate it. That make sense? If not, then you would be what? Your answer would just be this thing right here, and it's like, well, you know, without all that blue stuff in there. All right, well, we should probably talk about some new stuff, right? When's our test? This Tuesday? Oh, the 20th. Okay. Yeah. It's a week from today? Yeah, it's a week from today. Is it Tuesday? It feels like Thursday to me. All right. So 7.5. Areas or area of surface of revolution. All right, so let me try and motivate some of what this is about. In 7.3, we took a curve like this, and we rotated around the x-axis, right? Something like that. And when we did that rotation, we could ask what the volume was, right? We said the volume was pi integral a to b of the function squared dx. That was the first formula we ever talked about when it came to volumes revolving something. And it came from just taking that rectangle and spinning it around, right? And when we spun that around, we got this thing without a hole cut out of the center, just this disk, which is really like a cylinder. And we said that the volume of a cylinder was pi r squared h. For us, the h was what? Was this right here, was dx. The radius was the function's height, right? This height. And then pi came out. So that's where that formula came from, right? Remember that? Okay, now what we want to do is we want to imagine revolving that thing around the x-axis and not looking at it as a solid, but looking at the outside surface and trying to find the area of that surface. Totally different concept, right? Volume is a three-dimensional thing. Surface area is more of a two-dimensional thing. Or I could say if I wanted to fill this room with water, that's a volume, right? If I wanted to paint the walls, that's an area. So this formula gives us how much would fill the inside of that solid, but we want to know how much paint it would take to paint the outside. Make sense? Okay. So let's try and generate the formula. And once we have the formula, we'll just use it. All right, kind of like with the arc length. Just try and convince you why the formula works. So for the surface area, imagine that you have this graph. You want to know what happens when you rotate it around and find the area. So let's take, I'd like to take an infinitesimal little piece of this, all right? That right there. And I'd like to wrap it around, just that little piece, I'd like to wrap it around the x-axis. So when I wrap that around, I've got my little arc here. It gets wrapped around. Comes back up, you know, like that. Kind of like a rubber band looking thing, right? Goes around. And I'd like to know what the surface area of that is. You believe that? So to do this, what we can do is take our imaginary pair of scissors, right? And just cut this rubber band open and lay it down on the ground. So imagine just coming through, cutting that rubber band right there, and laying it down on the ground. What we'll get is this. This rubber band on the ground. We kind of exaggerate it here, right? And now I want to come up with a formula for the area of this, which is roughly a rectangle, isn't it? Now, roughly. So what is the area of a rectangle? Length times width, right? Length times width, or length times height, or however you want to look at it. It's one side times the other. So let's talk about these sides. This long side, right, is very similar to when we had the, remember I said you take a circle, you cut it open, you lay it down, and this side would be the circumference of the circle. Same exact thing, right? This length will be the circumference of that circle. That circumference is dictated by the radius, and the radius is actually the function's value. Yes? So this side should be exactly what it was when we were doing the shells method, which, well, same concept. This would be distance from here to here. That's our function's value, f of x. So circumference is 2 pi r. So this should be 2 pi what? Radius for us is the function's height, right? Are y'all buying this or not? Yeah? That's how long it is. This is the only tricky part of the problem. I mean, not saying the only, maybe that's tricky too, but this is the trickier part of the problem. How tall is this rectangle? Well, before we said that that little infinitesimal width was what? Dx, right? But see, that up there is not straight, is it? It's not straight. It's kind of got a curve to it. So what we're going to do is we're going to approximate that length using what? The arc length. Right? Isn't that little from there to there, we can approximate that as an arc length? Well, what's the formula that we developed last class for arc length? The arc length is the square root of 1 plus the derivative squared, right? Okay, that's what this side is. It's the square root of 1 plus the derivative squared. And so the area of this is this times this, isn't it? This times this. And then if we want to add them all up, we pull in the integral, right? And we go from a to b, which in our case will be our limits on x. And that's where the formula comes from. So here's the actual formula, if you're just one of those formula people. I'm going to put SA for surface area equals the integral. I'm leaving a little space there. Why am I leaving this space? What was in there that I can pull out? 2 pi, right? It was 2 pi times the function's height, right? Which was f of x. That needs to go in the integral, right? So you could put f of x here, and then times the square root of 1 plus, I'm going to write it this way, f prime of x squared, just so you have a different notation for it. F prime of x is going to be basically the same thing as y prime, right? So what's the difference between the arc length formula and the surface area formula? What's the only difference? Yeah, you multiply 2 pi on the outside, and the f of x goes in front here. There wasn't that before, right? That wasn't there. It was just the square root right away. So that's the only difference in the formula. Okay? So let's apply it to a problem. Oh, here we go. This will be fun. Maybe, if it works. Should we just go for it? Like I said, I'm winging it today, but I'm just curious if we can find the surface area of a sphere using this. We'll see. Hopefully our integral will be integrable. All right, find a formula for the surface area of a sphere with radius. Do you want to do radius like 1 or 2 or 3, or do you want to do radius r, where it's like we're going to get the general formula? I'll let you choose. Okay. General? Okay, radius r. All right, so what is the formula for the area of a sphere? I think that's volume. They're on your formula sheets. It's on the first page. 4 pi r squared. 4 pi r squared is what we should get as the answer, according to the book, right? 4 pi r squared. Let's see if we can get that. So if I was going to try and do this, I would imagine that a sphere is just a half circle, semicircle rotated around the x-axis, right? That's a sphere. Top half of a circle, rotate around the x-axis. But I could just look at the first quadrant and rotate that around the x-axis. Do y'all remember when we did this for volume? I proved the volume of a sphere. Do y'all remember that? Okay. I'm doing the same thing basically, but now we're doing surface area. So my drawing is going to look like this. I'm just going to look in the first quadrant. I'm going to get a quarter circle here. Ooh, that's a pretty good circle. Well, it looks better on my page than up there. The aspect ratio of that is different than this. So like this is the most perfect circle I've ever drawn in my life. Up there, it doesn't look that great. I heard somewhere that like in the old days, like in China, if you tried to draw a circle, you would be executed or something like that. Or it was like if you try and draw a sphere. Did you ever hear that? It's like the Chinese believed that the sphere was like perfection, so anyone who tried to like duplicate it was executed. I don't know. I read that somewhere. All right, do you agree with my picture? Do you agree that if I rotate that around the x-axis and find its surface area and double it, I'll get the surface area of the sphere? Yes? All right. Well, I need to find what this function is, right? Y equals what? So the way we did this before is we started out by looking at the general equation of any circle centered at the origin, radius r, and this is what they all look like, right? X squared plus y squared is r squared. You remember what we did now? If I want to know what y is, what we did with that equation? Solve for y, right? Solve for y. So I took this, I moved the x squared over, I took the square root, and then I didn't have to worry about plus or minus because I'm only looking in the first quadrant, which means my y coordinate has to be a positive. So the positive, that right there, should represent this right here. I can already tell you I'm not too optimistic about this. All right, so this, I don't think that's going to help. Because, well, let's not get, I mean, let's keep going. I don't want to give up because it's got square roots. I think it'll work. I know it'll work at some point in this class. I'll be able to prove it to you. I just don't quite remember if it's now or if we get into polar coordinates. When we do polar coordinates, we'll knock this out, no problem. But let's just see. I'm anxious. All right, everyone agree that's the function? Yes? Okay, I need to take that and rotate it around the x-axis and find the surface area. So that will be what? My formula will be 2 pi. Right, the area, I'm just going to put a this time. 2 pi integral, where am I going to go from? What are my x values going to go from here? 0 to r. Remember, we're going to have to double whatever this answer is, right? Because we're only getting half the sphere. All right, and then we're going to have f of x, which is this, times the square root of 1 plus, right? Now I need to take the derivative of this and square it. So I'm going to do that on the side. What is, if we have y equals the square root of r squared minus x squared, the derivative of this is, first the chain rule, 1 over 2 times the square root of r squared minus x squared, then times The derivative of the inside, remember r is a constant, so the derivative of this would be what? Negative 2x. Okay with that? Derivative of the square root of something is 1 over 2 times that square root times derivative of what's inside. Now let me square this. Hey, maybe this won't be so bad. If I square that, my 2's canceled up here, didn't they? Okay, square that. So square, what was on top? On the derivative, what was still on top? Negative x. Square that, you get x squared. And then you square the bottom, what do you get? R squared minus x squared, right? So way up there in that root, next to the 1, I'm ready to plug in x squared over r squared minus x squared dx. Still with me? I think this is going to work. Come on, no questions? Why did I put 2 up there? Why did I put a 2 up here? That's wrong. It should be r. I don't know if y'all noticed this, but kind of a little off topic, but something I think is important. The difference between knowing something and understanding something. All right? The arc length formula, right, or the surface area formula that I just put up here, 2 pi integral a to b f of x times square root of 1 plus all that, right, is something that I don't have memorized, right, because I understand where it comes from. So I can always draw the picture, and I can always come up with a formula myself. Now, I kind of lie, because I do remember it, but I don't remember it because I need to remember it. I remember it because I've done it so many times. But understanding something means that you can actually come up with the ideas on your own, as opposed to memorization where you're just like, where do I go for that? So I think there's a big difference, like going on and being engineers or whatever you want to be. The big difference between knowing something and understanding it. I'm a bigger fan of understanding. Does that make sense? So I encourage you to try and go deeper than just the surface level on whatever it is. Maybe it's not math, maybe it's not calculus, but whatever it is that you do enjoy, go beyond just the surface stuff. Really try and understand what's going on. All right, back to this. What am I going to do? Give up? I'm going to get a common denominator under there because that's what I've been doing, and it's been kind of helping. So let's try and clean that up. Shall we clean it somewhere else and bring it back, or you want to keep writing it and writing it and writing it? Keep writing? Okay. So you do whatever you want. I'm going to do this. Okay. So when I get a common denominator here with the 1, I have to do r squared minus x squared over r squared minus x squared. So up here on top, r squared minus x squared, then I add x squared. What does that leave me with? Just r squared. So I have an r squared on top. I'm happy about that. Why? Because I'm going to take the square root of it. It's going to be r, right? Okay, on the bottom is the common denominator, isn't it? It's this, which is r squared minus x squared dx. Do y'all see it? This is beautiful. Look at this. Yeah, they're completely gone. So with this square root on the top and bottom, you take the square root of the top, you get r, right? You take the square root of the bottom, you get square root of r squared minus x squared. But that's exactly what I have right here. So they cancel out completely. Y'all see that? And since this cancels with this, the only thing left in here is what? It's just r, right? The square root of r squared. So this is just r, are you kidding me? dx. R is a constant, right? What's the antiderivative of r with respect to x? What's the antiderivative of 4 with respect to x? 4x, right? So what's the antiderivative of r with respect to x? Rx. But I've got a 2 pi in front. 2 pi Rx going from where? Let's see, 0 to R. Now replace your x with r, and what do you get? 2 pi r squared. And then replace your x with 0, and what do you get? 0. So your answer is 2 pi r squared. But that was only half of it. So double that answer, 4 pi r squared. That's pretty cool, huh? We got really lucky right here, didn't we? We got really, really lucky. So what if you wanted the arc length? Okay, just think about this for a second. If you wanted the arc length of this instead of the surface area, the only thing that would change in the formula would have been that this 2 pi wouldn't be here, right? And then this wouldn't be here, which would have sucked because then it wouldn't have canceled, right? And so what we would have been left with is an integral that looks like this. Integral still 0 to r. Would have had the r on top, but this square root down here would not have canceled. That r is a constant, right? I could pull that out. What would you use to figure this integral out? R is on the outside, 0 to r. How could you figure out this integral? Trig sub. That's a trig substitution. You have something that looks like, right, square root of a squared minus x squared. So you make the trig substitution. You rewrite the problem in terms of trig functions. You go through all that mess, and you would get it. And what it would turn out to be is basically a quarter of the circumference, wouldn't it? The arc length, that top right corner, would be a quarter of the circumference. Circumference would be, of a circle radius r would be what, 2 pi r? So divide that by 4, so you should get something like pi over 2 for this as a final answer. No, hold on. Pi r over 4. Right? What's the circumference of an entire circle? 2 pi r, and this is a fourth of it. So you would get pi r over 2, is what I meant to say. So even that would have been doable, just a lot more cal would have been involved here, right? All right. It's pretty exciting. I feel alone here. All right. Now there are ways to go around the y-axis and do the same sort of thing. I'm going to avoid that, but I will tell you that in the book they do those sorts of problems in example 2. If you want to look at it, I won't test you on that. So for arc length and for surface area, I will stay to rotating around the x-axis, and I'll never go around a different axis for arc length and surface area. Just x-axis, period. No shifting or anything like that. Now volumes, that's different. If you're going to use shells or washers, that could be moved around, right? All right, so let's talk about some applications. So we're going to move into, you want homework out of there? Sure, right. Page 397. Find the exact area of surface attained running on the x-axis. So how about 5, 7, 8, 11. Okay, 7, 6. Applications. more applications, all right? The ones here are physics related and engineering related. So I'm going to start with, there's a couple of different things I could talk about in this section. I'm kind of picking the things that I want to talk about. One of them, the first topic is the center of mass. Have y'all heard of that before? The center of mass? Okay, so what is the center of mass? Okay. Yeah, I've heard that sort of interpretation of it also. I mean, basically what we do is we take any object that has mass and we try and find where its center of mass is, and then what we can do is we can look at that entire object as just being a point, that point, instead of looking at it as being the entire shape. So we reduce the entire shape down to a point. Now, sometimes you don't want to do that, but a lot of times you do. So finding that center of mass is an important thing. Like this yardstick here, right? Our center of mass should be some point that I can balance this, right? Something like that. Okay, but if the shape is not so nice, it might be harder to do. Let me see, I wasn't prepared today. I have some stuff in my office I could use for this, but see what I've got over here. Oh, these might work. Oh, this will work. It's actually probably better than anything I would have found in my office. So if I have a two-dimensional sheet, right? We call this a lamina, right? This is a lamina. And we're going to be looking at what's called the center of mass of this lamina. But we have to make one assumption before we can continue, and that's we're going to regard this lamina as being homogeneous, which means that we're assuming that the density basically at every point is the same. So we know that's not true because this paper is, different. The particles of wood that were used here and the fibers here don't all match. So we know it's not perfectly homogeneous, but we can assume it's close enough for this, right? So everything we're going to do today, this is a homogeneous lamina. What we're trying to do is find a center of mass. So if this is a perfect rectangle, right, then the center of mass should be right in the center, right? So this way, x direction should be in the middle, and then y direction in the middle. So I should be able to balance this thing. Now I've got this weird edge hanging off here, but for a rectangular, homogeneous lamina, the center of mass should be right in the middle, right? Of course, not going to work. So I'll put two fingers so it looks like it works. Right? That's the idea. But what would happen now if I come in here and do something like that? Right, now it's still homogeneous, but now your center of mass is all thrown off because you've taken mass out, right, in certain places. In fact, you know what? Take a little bit more over here. So what's the center of mass for this? Somewhere, right? It's somewhere. Now, where is it? Now, there's a way to do it if you actually have the lamina in your hand. And all you have to do is just maybe get like a thumbtack. And what I'll do first is I'll just get my ruler here. And I'm going to hang my ruler so it's going straight down like that. I'm just going to draw a line. Close enough. Let's just say that's straight down, okay? That's pointed towards the center of the Earth, the gravity, right? The center of mass of the Earth is where that's pointed. And now I'm going to take this, and I'm just going to hang it from a thumbtack right up there Come here. Grab that. Okay, right? And I'm just going to draw this right on top of it again. Like that, okay? And I'm going to pick another point. Doesn't matter where it is. I'm going to hang it again from that point. And then I'm going to do a third point, just to be sure. I'm going to hang it from here. If I do that, it's your center of mass right there. Okay? So I have the center of mass of that. If I was able to, and this thing wasn't so floppy, I should be able to put my marker right there. Well, that worked pretty good, actually, right? It'd be more impressive if I did on this end. Hey, that's not bad, right? That's my center of mass. Now, what if I now take something else? How about this? There we go. Okay, so let me do this again real quick. I'm going to do this one real rough, okay? Goes like that. The next one, I don't know, looks about like this. And the next one, something like this. Well, what can you say about that? The center of mass is not on the lamina, but there still has a center of mass, right? But it's like a boomerang. A boomerang is an example of an object that has a center of mass that is not on the object itself. So you don't have, your center of mass does not have to live on the object. But if I have this weird shaped thing, and I want to talk about it moving through space or something like that, then I can just reduce it down to a certain point, and then take its total mass and just refer to it as a point with the total mass. Now, not for every application would you want to do that, but for a lot you would, right? So this one, reduce it down to a point, then this doesn't matter anymore. All right, y'all with me as far as the idea? Now, in a Calculus 3 course, you deal with laminas that are non-homogeneous, which means that you actually know how the density varies throughout the lamina, how it's different. So maybe over here it's more massive, more dense than it is on this end. And you can still find centers of mass that way. But that requires double integrals instead of regular integrals, which we do in here. All right. That's physically, visually what we're going to be doing, all right? Trying to find the center of mass of something. So let's first start out with trying to find the mass, period. I'm trying to find the page where this has this that you can refer to, because I'm skipping around in this section. All right. So let's say we're given some lamina. So our lamina is going to be this thing right here. I'm going to call it L for lamina. Now, I noticed that with this lamina, I did stick it between two functions of x, and I cut off the y value, or I'm sorry, I cut off the x values between two constants. So this is like a type 1 region, isn't it? When we were talking about integration, this is like a type 1 region. So the first thing we want to be able to do is find the area of this. Okay, so you find the area. Can you do that? How do you find the area? If I come in here and I label this function f and this bottom function g, and then we go from A to B. Put in there homogeneous laminas because we do need that. What is the area of that lamina? Because I'm going to give you the formula for the center of mass, but you need the area for the formula. So what is the area of that? It's the integral from A to B of f minus g. Right? That's the formula for the area. Does everyone agree? We should be able to do that before we came in here today, right? We've done areas between two curves. All right, so we need that. Now, the center of mass, I'm just going to give you the formula for it. The center of mass is always looked at as a point in two-dimensional space. It has an x-coordinate and a y-coordinate. Would you agree? It would have some x and y coordinate, but we don't call it just x and y, we call it x bar and y bar. All right, that's what our center of mass would be. Somewhere in there, I think we would all agree that the center of mass of this lamina looks like it would be in there. It wouldn't be outside of it, but no matter where it is, it has an x and y coordinate. Now, here's how you get each one. X bar will be equal to 1 divided by the area. In other words, you're going to divide by the area, but what are you going to divide by the area? This new integral, which is going to go from A to B of x times f of x dx. And then your y bar will be 1 over the area, A to B. Now this one's a little different. 1/2, which we could have pulled out, but I'm just showing you the similarities and differences between these two formulas of the function squared dx. So with arc length and with surface area, I showed you where the formulas came from, right? For this section, I'm not going to show you as much where the formulas come from. You can read through the book if you'd like. They do show how the Riemann sums will generate these formulas. I'm not going to. Let's just use them, all right? So when it comes down to it, if you have a homogeneous lamina and that lamina is really just like a type 1 region, to find the center of mass, you're going to need to find the area first. Go figure out what that is, get it, put it to the side, then go compute these two integrals, and when you're done, divide by the area. So let's do an example, yeah? Example. Find the center of mass of this region. Here's the region. I'm going to describe it to you. Your x's are between 0 and 2, and your y's are between 0 and 4. That's your region. So what is that geometrically? It's a rectangle. Since this is our first example, I'm trying to show you that these formulas are going to come up with a result that makes sense. And then we'll do problems where it's not so obvious. What do you think our answer for center of mass should be here? What point? The 0.12, the 0.12, right, out to the right one, up to, assuming that this is a homogeneous lamina. Let's see how those formulas verify that. So let's do the area real quick. Can you tell me what the area of this thing is? You could set up an integral, couldn't you? Let's not, though. All right, what's the area of that? 8, okay. Now, we do have a top function and a bottom function here, don't we? Right, the top function here, I could say f of x equals what? The constant 4 function. Then the bottom function, g, is the constant 0 function. Y'all okay with that? I'm only doing that because now I'm going to go find x bar, y bar. So I need to figure out what f and g were. All right, so here we go. X bar would be what? 1 over 8 integral 0 to 2, because that's our restriction on x. And then x times f of x, which is 4 dx. Do you all see that? It's x times f of x, but f of x up here is 4. And then we compute this. What's the antiderivative of 4x? 2x squared. And we have the 1/8 out there. And I'll go from 0 to 2. Plug in 2, what do you get? 2 squared is 4 times 2, you get 8, you get 1. You plug in 0, you get 0. So you get 1 for x bar. Good, right? That matches what we thought it would be. Okay, and then let's do y bar. So 1 over 8, integral 0 to 2. This time it's not x, it's 1/2, and then it's the function, right? What's our function? 4, and then we want to square it, then dx. 4 squared is 16. 16 divided by 2 is 8. Take that 8 out, and it cancels with the 8 out there, right? So all we get is the integral from 0 to 2 of what was still in there? 1 dx, right? We don't have an x in there? Right? Yeah, antiderivative, correct. So we do the antiderivative of 1, and you get x, and now you evaluate 0 and 2. You plug in 2, you get 2. You plug in 0, you get 0. So your answer is 2. That all makes sense? Yeah, any questions? That's just to verify that the formulas appear to work, right? I mean, that's definitely not, the way we go about proving things in math. By just showing it happened one time doesn't mean it's always going to happen. But at least we feel good that it worked at least once. Now, let me go back to this previous page. What I want you to do here, I want you to correct something on this, only because I got ahead of myself here. I was giving you a formula that was a little more general than what the book does. Sorry. I would like for you to go in here, take the g out, because they don't do that to you. They just look at the lamina as being below the f function all the way to the x-axis. So they are always taking your g to be 0, right? Your g is 0. So this lamina goes from here all the way down to the x-axis. The area is just then f of x, no minus g. And then this formula works. Is that all right with you? I'm going to tell you a quick story before we do a real example while I'm thinking about it. There was this competition at MIT. Y'all know where MIT is? Or y'all have heard of MIT, Massachusetts Institute of Technology? Okay, it's supposed to be a very prestigious college here in the United States. And this happened many, many years ago because I heard about it when I was a student. Some class, I don't know what it was, the professor asked the students to try and estimate the area, the square miles, okay, how many square miles the MIT campus was. And he broke out the students into groups and said, okay, you've got a couple of weeks for this project, you know, however you want, try and estimate the square footage. So everyone had these different ideas and how to do it and everything else, right? So the winning one, okay, you want to know what the winning group did? Is beautiful, right? Because a lot of groups went out and like tried to like measure things, and this is before like laser rangefinders and, you know, but they were out there with like big old tape measures and trying to like actually go around the campus and construct polygons and find this area. All right, so what they did, this group that got the closest, is they took a map. They took a map of MIT, all right? Folded it out. And so that map, let's say they laid it out, right? And then let's say this was, the MIT campus, let's say was some weird shape like this, right? So what they did is they said, all right, they broke out their ruler, okay, and they measured the map itself. And let's just say it was 30 inches by 20 inches, let's just say, right? Got it? And then they weighed it on one of those like very, very accurate chemistry scales, like where it gets down to like the, you know, very, very precise, right? They weighed the entire map. So they know the area of this would be what? What's the area of the entire map? 600, right? So they know that the weight of the map, which they knew that, right? Divided by the area of the map must be equal to, the ratio must be equal to the weight of the campus, C, over the area of the campus. So then they went in, they cut the campus out of the map and weighed it. So they knew the area of the map, the weight of the map, and the weight of the campus. And they solved for the area of the campus. And then they converted everything over to, you know, miles, square miles. Didn't even have to go outside. That's pretty sweet, right? So when I was buying my house, I had a choice of 2 lots. And the square footage didn't make sense to me. Like the drawings didn't look right. The lot next to me looked smaller, but the listed square footage was larger. It was like acres. They did in acres. And so I actually did the same exact thing. I had heard of this. I didn't come up with it on my own, but I did the same thing. I took the surveys of the lots and I cut them out, and I came to the chemistry lab over here and I weighed them, and so my lot's like maybe like 2/10 of an acre bigger than the one next to me, so that's the one we chose. Plus its orientation to the sun where it rises and stuff, but you know, it's pretty ingenious. I like this. This is good, right? So imagine how pissed off those groups were that were out there for like hours and hours and hours and hours and hours doing this, right? Now, what did they assume here in order to get this? Like they had to assume the map's homogeneous, right? And it was homogeneous enough, okay? Because it wasn't, I mean, it's not a perfect paper, but it was so close to being homogeneous that they were still way closer than anyone else got. Interesting, right? All right, let's do one example, and then we'll call it a day. It's another word for center of mass, centroid. So find the center of mass or centroid of region bounded by y equals x, oh no, I don't want that. Y equals 2 minus x squared, and y equals x squared. Or y equals x, pardon. All right, so here we go. Our drawing, 2 minus x squared, looks like this, parabola, right? Y equals x is the diagonal, right? I want the region bounded by the 2. It's this. I want the center of mass of that. What's the first thing you need? The area, right? But for the area, I need to know the points of intersection, right? I know which one's on top, I know which one's on bottom. This one is the 2 minus x squared. This one right here is the x, y equals x. So how do we find the intersection? We set them equal to each other. 2 minus x squared equals x, which means x squared plus x minus 2 equals 0, which means x plus 2x minus 1 equals 0. So our two solutions are 1 and negative 2. That seems to look right, doesn't it? Negative 2 here, positive 1 out here. So give me the formula for the area. Area is please don't be shouting over each other like that, okay? Raise your hand. Integral negative 2 to 1, 2 minus x squared minus x. So look, we are extending what we've been doing. So we are taking into account an f and a g here. Even though the book doesn't do it, we need to be able to extend the idea out to, okay, we do have a top and a bottom function. We know how to find the area of that. So that's it right there. I'm trying to save us a little bit of time because I'm almost out of it. It was integral from negative 2 to 1 of 2 minus x squared minus x dx. 9 halves. So this turns out to be 9 halves. Just double check it here. 9 halves. All right. Now for the x bar, y bar. For x bar, I'm going to have 1 divided by the area, right? What's 1 divided by my area? It's really 2/9, right? So just flip it, 2/9. Integral, I'm still going to go from negative 2 to 1, right? Of x, which is just x. But what's f of x here? Yeah, it's the f minus the g. You have to still do that because it still represents that height. And for us, the height is the f minus g. G in the formula is 0, but we're taking into account that the bottom's not 0. Okay, so this will be the f function 2 minus x squared, then minus the x, and then dx. So all I'm going to do is go back to Mathematica, and I'm going to throw an x in here, and I'm going to throw 2/9 on the outside. So I'm going to throw an x in right here. And then I'm going to say out here, 2 divided by 9 times. So I get negative 1/2. So this becomes negative 1/2. Do we feel good about that answer? And look at it here. -2, here's -1, so negative 1/2. We're saying somewhere around right here is the x-coordinate of the centroid. The next part should probably maybe be up a little bit. I don't know, we'll see. Okay, now for y bar, we're still going to have the 1 over a here, which will be 2/9. And we still have integral -2 to 1. But now the formula changes. We have a 1/2, and then what we're supposed to have is the f function squared. But because our region actually has an f on top and then a g on bottom, we need to be real careful with this. This will be, I'm doing it in brackets, it'll be the f function, so 2 minus x squared, then take away the g function, x squared, then dx. So you would actually have to expand this all out, and then you'd have to combine it with this, and then go ahead and finish computing that integral. If you do that, then you should get, let's see, I already had Mathematica do it, so 2/5 is what we should get here. Now, because of this because of this mistake I made in class, I want to make sure that you're aware of the 2 formulas, or actually 3 formulas that we have for the centroid. We have that if you want to try and find the center of mass, I don't know, I'm just making this up, if that's your x bar, y bar, then to actually do it, if you're looking at the lamina between 2 functions like this, then you're going to find the area first, which is this integral. So it's integral a to b of the top function minus the bottom function. Figure out what that is. Now your x bar is going to be 1 over that area, integral a to b, and then it's x, and then times the difference of the 2 functions. So same thing as this, but just throw an x in front. And then on your y bar, 1 over area, 1/2, and then it's your f function, whatever that top one is, square it first, then subtract from it the g squared. What I did in class, it's just a brain fart, I did f minus g squared. That is not equal to f squared minus g squared. So that was my mistake. I'm correcting it here in this video. Hope that makes sense. I send an email out to correct that also. But all right, that's it.